Next speaker is Taegun Song. He will give a talk about the machine learning.
Okay, good morning everyone. First of all, I would like to thank for the organizers for inviting me to some kind of impressive workshop. So, okay, today I'm going to talk to you about machine learning. And then, my name is Taegun Song, and I came from the Department of Data Information and Physics in Hongju National University in Korea. Okay, just So here is my outline. So first of all, I'm preparing for the students for the introduction to the machine learning. Then talking about the relation between physics and machine learning. Then I was showing the two examples what I have done 2 years ago. Okay. So this is the conventional approach to the how we sense making from the data analysis. So here the schema, which means some kind of structure of our knowledge, they updated and debated from the model and data. So this is kind of conventional approach to the making our data analysis. And then each model have their own specific models are used to apply it. So recently the much attention machine learning attract much attention to this trend approach, say model-free data analysis. So it's just not for the model, we are just taking some tasks. So, so first is about what is the machine learning. There is actually no rigorous scientific discussion of definition for the machine learning, but this is commonly we use it to define machine learning in this way. So first of all, it's a kind of the computer program. So what is the program? So we have the building some computer programs, and then we put the inputs, and then program generate output. That's just computer program. And then the machine learning, in order to the machine learning, we have the task, and also this performance measurement. So what's the task is that, so task makes the desired output. So the performance can be measured at the difference between the program's output and our desired output. So we can define this difference mathematically. And the most important thing is the improve with experience, which means that we iteratively input the data again and again. Then we can decreasing the output, program's output, heading to our desired output. That is the machine learning. So in short, the machine learning is the study of algorithm, which the machine can produce desired output. The desired output is depending on the person making. So one example is that the machine learning is let's make the machine to counting the object. So there is some program. So the program is just printing a number, and then we put the data set. And that program is just printing a number. So just whatever some count. The output was 2. And then that is the desired, it's not our desired output. We are counting the 3 apples, so we want to, the answer is 3. So we can, making this, let the machine know that is too small, which means that we can just adjust the parameters inside the program. Then next trial, then they put the 4. Then, that is too big. Again, that's just the parameter. This is the procedure of the running. Then finally, they put the output 3, then we can, okay, that parameter is fixed. Then we are teaching the machine, which that have ability to counting object. Then we can, and then we are testing some different domain of the data as an input to the machine. And if hopefully this machine put their output as 2, then we can say, oh, it's now we are successing to the counting object. It's a good generalization. So most of the case, and then if they do not that kind of testing, so which was this testing data is unseen data during the training. So and then that kind of problem is so-called underfitting or overfitting, and then that in that kind of things we can resolve it by technically. It's just nothing but just technical. So why we are using this machine learning? Sometimes counting this apples, so machine is much faster than person. And this is a little bit hard to the machines. But if we can make this machine more very sophisticatedly trained, and then we can now counting these dogs from that figure. Actually, half is muffin and half is dog. So what the point is that, so if we are using the machine learning as a useful tool, then the most important thing is actually data pre-processing and then feature engineering. So those two procedures definitely making the quality of the machines. So actually, in short, the machine learning is nothing but just optimization, either some data analysis by the optimized parameters in the machine by using the algorithm. There is a bunch of the way to this learning way. So depending on the data set, we can apply the supervised learning or supervised learning, something like that. It only depending on the input data. So why do that kind of cartoons are showing that in the island, the woman's isolated, and then she wanted to be helped, but no one knows. But I know machine learning, then everyone into that. So recently, this is a very hot topic, and then we can use machine learning. So if we actually AI, so artificial intelligence is we can sort it some kind of field of study, then we can divide by two. So hardware and software. So hardware is just real hardware. So recently some quantum qubits are the neurologic processors, and then a bunch of trials also in hardware. But machine learning is nothing but all the software part of this AI field. And then there is a lot of machines, so decision tree, there is some Bayesian network, soft vector machine, Boltzmann machine, and then most successful in the artificial neural networks. And then if we are making that artificial neural networks, making a deep architectures, and then it's so-called deep learning. So the deep learning is just a subset of the machine learning. Okay, that's an intro. Now I'm talking about the physics and machine learning. So you can recognize this some kind of map. So this is actually the map from papers from the archive. So each dot, actually this is a dot. One dot is one paper. The size of that is the citation of this paper. So this data was on archive with 1.7 million papers now currently submitted on the archive. So in archive we can classify the category. So I can name it each lab. So here the lab white dot is the paper which have the machine learning in the title. It's only selected 500. So all over the world, all over the physics world, they are spreading some machine learning technique. Then I have also the 3 flags there, so 2 in quantum and 1 in biological physics. And currently 2 more, but so why this AI? Actually, AI was just for the industrial successful, but currently, academic society we are actively adopting this technique. So actually, AI maybe no one very specialized to recognize and generate the patterns. Then also usually this AI requires lots of abundant data set. And then currently we so-called the big data era, so everything is satisfied. And then paradigm shift means that at first AI is appearing and the industrial they are just adopting this AI without any mechanism. So just we are so-called learning by doing. Just train some kind of machines and then it's successful, then that's okay. So no one curious about why they are successful and then why we have to use that. No one asking that. But currently, there is some kind of the new trend. So explainable AI, either some trustworthy AI. So nowadays, the researchers are going to move to using this mechanism. And then actually, the physicists are very uniquely situated from the benefit in this field. So the Basel underlying concerns are they adopted from this our in physics. So maybe as physicists, why don't we using this machine learning technique? So and actually. Also, the physics also in this AI field, we are contributing some lots of understanding to that. Then the field was the energy-based model. We can thinking this the algorithm was minimizing the free energy. That we can exactly mapping on the relations, and either the physics informed and the physics enhanced. So we can just put some physics law. Such as so energy should be conserved, either some kind of restriction, that making the much better machine. So also the quantum field. So today we are talking about the quantum physics and then AI. So actually there is some kind of not rigorous definition again, but we can divide by the algorithm types from the classical either quantum, and then also data from the quantum either classical. So if one can thinking that quantum physics, AI, machine learning for the quantum physics, we have to be used to quantum data and with quantum algorithm. But that is not essential. So we can apply the classical algorithm to the quantum data, and also the classical data by using this quantum algorithm. That all the possible combination is So today I will talking about this just application, just kind of a useful tool to the quantum system. So I was preparing two cases for the analyzer and simulator. Each one I was motivated from this pattern recognition and pattern generation. And then why we are using this machine learning into the quantum system? Just the benefit was, first of all, we can speed up because of the quantum calculation, but we can replace the artificial neural net, and then speed was very remarkably faster. And then also very cheap, and yeah, sometimes we can extend some large systems. And also in the other direction, so as known as some quantum artificial intelligence, which was there now we are qubits and the quantum processing, quantum information. They also actively finding. Okay, from now on I will introduce my previous work. Quickly before the lunch time, so I'm trying to run. So if you have any questions, and then please don't mind to hesitate. So okay, first of all is analyze. So everyone have a cell phone, and then if you can cover the thin film on our cell phones, we can make bubble. That actually the master hands they can avoid, but I hope to say it's unavoidable deformation. So it's the same on the graphene. If we making the graphene nanoribbons, we can find the bulb, the white bulb. Actually, the bulb is the defect, so it's not good for the electron conductivity. And also, in other way, that is not normal defect. So the nano bulb will induce a very strong pseudomagnetic field. If you have some kind of knowledge on the graphene, then there are some pseudo spins. That pseudo-magnetic field of order of 300 Tesla is very amazing. So we can often that strain engineering in this as a defect, either as a source of strain engineering. So nanobubble recognition is needed in this field. So, why they? So from what and how? That's our research objective. Okay. So first we are calculate the electronic structures due to the bubble. So if some experimentalists, in order to find this bubble, they have to look nearby lines. It's like find a needle on the sand. So it's really hard. And we can just model it just Gaussian bond. So we have two parameters for this now bubble, for height and width. A single bump there. And then some kind of packages we can just obtain this density state. So by applying this the current, then we can easily measure this current. So our idea is that input data to this dose, and then they are inferring some height and size of the bubble, analyzing this bubble. So we are preparing some data sets, varying this height and width. So theoretically, we obtain 73 independent spectra from just
the quad package is that created by Antoine?
Yes. So, okay, when we are processing this ML machine learning technique, there is some kind of two difficulties. So first one is to choose a number of data points. So actually, this is very fine structures and then the very sharply peaked theoretically. So in order to catching that peaks, we have to need very fine resolution. So that makes because of the huge dimension of the input, make the huge computational cost for the machine. And the second one is the too small to train the data set, only 73. So how we can overcome in this? Just the first one is just applying this interpolation, changing to the 2 magnitude was decreasing, and then adaptive. We can thought that if this is theoretical, but for in theory we have only one specific parameters and then one dose curve. But if we are measuring this, what if it is experimental data, then we can unavoidable the white noise. So we just considering additive white noise into our dose spectra, then preparing the bunch of data set. So this is our schematic figure. So the red one is the ground truth. And actually, the sigma is 25 and H0 is 13. And then we adding this white noise. So black hole was our input to our machine. And then our result was a sigma is inferring 24.696 and then 12.99. So it's quite close to the real value. And then that is all, and every data we cannot be replied, so we just represent, decide this representative quantity for just the systematic comparison, which is the maximum pseudomagnetic field. That's scaled by H02 or sigma cubic. So our machine performance was quite amazing. So they are within this the red line, which means that our truth value and prediction value was exactly the same. That they are located on the red line. So it's quite nice. So there are two some different points, but yeah, almost all case we can find these real ground truth parameters. So we can one interesting thing is that depending on considering the additive noise, so one can asking me this amplitude of this additive noise, how can they affect to our machine performance? So we can just increasing that. So the eta equal to 0 was ground truth, and then if eta equal to 0.1, 0.2, that is 0.2 was almost peaks, small peaks are smeared out into the noise. So we can measuring this absolute percentage error for the height and so less than 10% or 5% of the height and almost 10% of the width. So the machines can be possibly to detect this nanobubble. That's our conclusion. And okay, so let's move to different way. So yesterday, Dr. Moon was nicely introduced continuous time quantum Monte Carlo. So again, I just briefly talking about that. So quantum Monte Carlo is kind of the method to resolving quantum system. Then there is a bunch of various techniques that exist. So we are just picking some passing integral Monte Carlo family, then continuous time quantum Monte Carlo. So there are actually two ways to expanding our partition functions, interaction expansion and hybridization expansion. We are on this interaction expansion. So actually, this is not important anyway. So all the procedure was like this. So we are initialized and then update the Monte Carlo sampling. The red box area was most of time-consuming part to the sampling of the Monte Carlo. And then again, that kind of thing. So okay, we just replace this red area by the Majorana. That's all. Actually, there is no physics, just replacing. So, so why we are considering this one is this continuous time Monte Carlo is that they are giving our the green function, and the green function can be converted by this spectral function, which was real observed in our real. So we just the seed of this tau k, which was the imaginary time in the continuous time Monte Carlo, and then output is just green function. Then we just preparing the sample and then just matching by tuning this the auditorium of the structures. So that's provided this avoid the Monte Carlo sampling and matrix inversion. So that matrix inversion means that if we want to calculate these green functions, and then here the m. Okay. that's some kind of numerical. Computation limitation came from this. Most of the time we came to this matrix inversion. So we just replace that. So put the tau k and then get the green function. So our result was really amazing. That means exact is continuous time quantum Monte Carlo result. And then CTQMC plus ML was we just preparing this tau case from the Monte Carlo, and then obtaining these green functions by that neural net. The first we are just non-interacting case, and then nicely match it. Then we do not need that not much of the data. It's just order of 10,000, and that's enough to inject reject. Okay, and then that is autoencoder was actually I was deleting the introductions, but autoencoder was very specific structures, which means that we are training these two parts. First, we are data provided here and here. So it's a singly occupied and doubly occupied. It's a weak interaction and strong interaction. And then we can tune this our machine by the interaction strength. So this again this real exact data and then the machine hybrid method, they are quite nicely matched. So we can predict this double occupancy on our system. And finally, we can testing the various cases away from the Hopf filling and then the other quantities, not for the green functions, for vortices. Then recently we have some kind of motivation that this machine can be applicable to the quantum Monte Carlo cross dynamic density matrix functional theory. So now we actually are finding some kind of positive result. We if you want, then if you're curious, then just read that archive papers. So okay. So I would like to summarize it here. So I just want to gave you the take-home message, which means that machine learning is kind of just a useful tool. So we do not worry about their mechanism and how they are worked. It just can be used as a tool. Then I was showing these two examples. So you can, if you're interested in each topics, and then you can find our papers. Then again, I'd like to thank to my collaborators and then my former scientific advisors. Then most of all, really thank you very much for your kind attention.
Any question?
Thank you very much for your interesting talk. I have a very general question. When you talk about at the beginning about apples, so can we say that machine learning is, since we know the outcome, we could adjust the result, 2 apples, 3 apples. So we can say that we can use it only when we know the outcome. Can we use the machine learning something that we don't know the result? Then we cannot adjust. So how
Okay, so the first of all is in that case. So if we know the answers and then questions, that's we are so-called supervised learning. We are training by answer and questions, and then suddenly we can just asking them, and then they can answer. The second one is the unsupervised one, which was there is no answers. We just put the data, and then what the machines do is that they just we so-called clustering. They just collecting these similar data sets in together. Then after that we can this is if we just bunch of 6 million of dog and cats photos, and they just put the neural net, then we prepare in some several nodes, and then at certain time, so one node there is only cat, this node is only the dog. Then which means that they do not know what's the cat and what's the dog, but they are just clustering. And so yeah, depending on this data type, so there is a bunch of this learning method, and then you can improve.
Thank you.
I'm curious about the input. What is the input for the CTQMC? You just show me this tau k, but does it mean different combination of segments, or so what does tau k mean for the input?
Okay, honestly, I'm not expertise in this field, so actually everything, something like I'm expertise in AI, and then there is so Professor Humpyo Lee, he was expertising in this continuous time quantum Monte Carlos, and that the tau k means their expansion of this imaginary axis. Then
I guess it's a combination of creation and annihilation on the imaginary time axis. Okay.
and so actually, in order to this continuous time quantum Monte Carlo, we have to the diagrammatic expansion. And so tau k and k, for the given tau k, we just given tau k and then green functions just to match.
Generally speaking, machine learning provides a tool for solving of complex, complicated problem that optimize the solution of a given complicated problem. Right?
Yes.
It probably doesn't increase preciseness or accuracy, but just provides some optimal one-dimensional Schrödinger equation, or many particle Schrödinger equation. But in addition, there is quantum information science, where in principle one can develop machine learning tools also. So as I understood, you mentioned it. What you mentioned was using classical machine learning in quantum physics, right? Not quantum machine
Yeah,
learning.
currently I'm ensuring this classical machine to the quantum
I see,
system.
I see. And the last question, well, you mentioned quantum package by Antoine Schneider. Well, I saw, I participated, you participated together in different conferences. He always advertises this machine, quantum package. I did not know that he started to use machine learning. Did he already included machine learning into his package? Did you mention that? Or maybe mention it quantum?
I think, okay. So there are actually a bunch of hierarchical classification for the two machine learning, and then the other is a discriminative and generative model. So each are little bit different philosophy. So such as some supervised and unsupervised, similar to that in that way. So for the quantum information, there is also so mainly people have thought that this Shor algorithms and then that kind of thing also belonging to the quantum information.
Yes, yes.
And also
It's called quantum algorithm, actually.
yeah, but in here I mean is just if I think machine AI as a tool to investigate some quantum system, then there is we don't need to actually real quantum algorithms inside there.
Just
So
classical.
so that's enough to our data analysis.
I see, thank you.
So,
Any other question? Yeah.
So for that, you need training data. Do you need, or without training data you can use this machine learning? I think
Tuning the data. Does one need to tune the data? Data tuning is needed or not for machine learning?
I think maybe tuning means data pre-processing. We so called that. So if you train some machines and then you have a data, and then there is also some way to how can I use this. So you can manipulate your data as you want. So that's why the physicist can be strong in this field. So just the computer science guys, they are only focusing on this algorithm. How can we fast and how can we cover some big data, something like that. But physicists are always talking about what's our task, what I want to get by using these machines, and then what I have this. Then then naturally we can think about how we can manipulate our data in order to easy to extracting this our desired outcome. So yeah, so tuning means so some kind of pre-processing, and then that usually enhance the performance of the machine.
Yes, pre-processing means outside of the black box, right?
Yes.
When
Yeah.
you put it into the black box doesn't need this tuning.
Yes. But interesting is depending on this data pre-processing.
I have simple question. In the introduction, you talked about the supervising learning case. In the case, what's the difference between supervising learning and conventional feedback process? It seems to be similar to the feedback process. What's the crucial difference?
What's the differences came from the adjust parameters. So we can okay. So this loop feedback and adjusting parameter, it's not by hand. It's just own algorithm that makes machine learning techniques.
You need machine.
Yeah, itself they improved itself. Yeah.
Thank you. Any other question? Okay, if there is no more question, let's thank the speaker again. Next is lunch time. Where is lunch place?